Yes.
Okay. So look at a couple of problems from Klepner only that discusses how you can apply work and energy. But before I get into it, so there was one question as to how work energy helps you solving Newton's law. So Kunal has briefly, I mean, he has sort of already answered the question, but and we'll also look how it's helpful through these examples. But so I'll just briefly get this out of the way. So what Newton's law does is, provided that you supply a force, okay. So this is Newton's second law, and this is a second order differential equation, and you need to solve for x of t, right? This is what it means solving this equation. You need what x of t is, and you also are, let's say, interested in terms like the velocity. So this is x dot is dx dt is the velocity. And to solve the second order differential equation, you will need initial conditions too. So you supply some position and some initial velocity, right? Now, this is a second order differential equation. So in general, it's going to be very difficult to solve. However, as you have seen, Kunal has discussed that he started from this equation, right? And he multiplied both sides by dx. So f of x dx, and after you integrate this, you get the work energy theorem basically. And this gives you an equation of the following kind: dx squared plus potential, and this is some constant, let's say E, right? This constant is determined by your initial conditions, right? So you provide what the initial position was, you provide what the initial velocity was, so this gives you the kinetic energy. This also gives you the potential energy, and you can find what E is. Now, the advantage of this equation is that you can directly find what dx dt is, right? This is some root over something. So root over e minus u of x, some factors of 2 and everything. So once you have this, then calculating x of t is very easy, because here you only have to just integrate this directly and you'll get what x of t is times this function root over e minus u of x. So it is in that sense, I believe Kleppner meant how you can use this conservation of mechanical energy to solve the Newton's laws. Because in general, if you want to find x of t and you only use Newton's laws, then it's going to be very difficult because you need to solve this differential equation. But working with Newton's laws and working with this mechanical energy conservation is exactly the same, as you have seen that you can start from here and you can derive this equation exactly. So you can just use this equation to solve for dx dt, and this then allows you to solve for x of t. So I hope this part was clear.
Yes.
Okay. So we'll also see some examples how it can be useful in other cases as well. Okay, so let's start with this problem. This problem has a mix of Newton's laws and energy conservation. So I think this is illustrative. So the problem is as follows. You have a ring. Okay, and let's say this is the center. This is radius and all. And you have two masses attached which are moving. So they start from this position, both of them, and then they start moving in opposite direction. So at any instant of time, they're at a certain angle theta. And so the problem is that we have to show that this ring will start to rise if, so the mass of the ring is capital M. If you have M greater than 3m by 2, then the ring will start to rise because of these motions that are all happening. And we have to find the angle at which this occurs. So you have to find the limiting angle at which the ring starts to rise. So let's first understand how this entire process can happen. So the first thing we have to look at is all the forces and the free body diagrams. So again, to avoid any confusion, the best thing to to do when drawing free body diagram is isolate the bodies and focus only the forces that are acting on individual bodies. So let us start with the ring. So what happens for the ring is you have a tension T that is pulling the ring upwards. So this tension is there to balance a lot of forces. One obvious is the gravitational force due to mass of the ring itself. And we can assume that the entire mass of the ring is concentrated at the center, right? This is sort of the center of mass of the ring. And because you have these small masses, and there's a contact between the small mass and the ring itself, so they will exert normal force onto the ring, which will be perpendicular to the surface. So this is the surface, and the perpendicular normal force will point along the center. And again, I can draw perpendicular for the other mass as well, and they will point along the center. So I have two normal forces because of the contact forces because of these small masses. And for now, it seems these are all the forces that I have. Okay, so we can resolve them into various components, and let's see how these act. So based on this description, we clearly have, so we can write an equation along the y direction. So you have the tension that is trying to pull it upwards. We have the gravitational forces, and in the equilibrium case, this has to be balanced with the vertical component of the normal forces. Right, so this is for equilibrium. Right, so if this is theta, this is also theta, and so this is n cos theta. And we don't need to write the horizontal equations, but you can see that these get cancelled due to these components. Both of them are equal and opposite. So this is the first equation that we need. And we can write the same for the smaller masses. So we can, since the two masses are completely symmetric, we can focus on only one of them. So let's look at this one, for example. Now, the small mass exerts a normal force onto the ring along the center, and so because of a reaction of an equal and opposite reaction, we'll have a normal force that this mass will act along the opposite direction. So again, this is the surface, and this will be the perpendicular. Plus, I also have this gravitational force that is acting downwards. The angle is theta. And so I can write the equation here. So this will be mg cos theta towards the center minus n. And remember that these masses are also moving with certain velocity, right? So they start, so in this setup here, they start from in this position where velocity is 0, and then they start moving. So at any instant, they're moving in the circle. And because of their movement, because of the circular motion, we know that there's a centripetal acceleration towards the center. So this entire thing has to be equal to the centripetal acceleration. So we are through our first step, that is to understand how the forces act onto each of the bodies. And now if you notice that we have a couple of unknowns. We have the normal force is unknown, the tension is unknown, and we also have a velocity here. And these are static equations, so there's nothing to solve. For example, there's no acceleration, so you don't have a differential equation of this kind. So you can't really move forward from these two equations, and you need to use one more extra condition, and that comes from your energy conservation. So in this entire setup, there are no dissipative forces. Like, it is assumed that there's no friction and everything. So you can safely use your conservation of mechanical energy. And that will give us what this velocity is. So this is, let's say, a third part, conservation of energy. This is 0, and so they start here, and the bits come up to, let's say, this point. Now the potential energies in this case is due to the gravitational potential energy, right? U equal to mgh, and this h is the vertical displacement that this masses have suffered. So from coming from here to here, the vertical displacement is this. And this we can easily compute because H is, so this entire thing is R. And you can subtract from R this portion L, right? L also you can find that, so it is R minus L. And L is nothing but R cos theta that you can get from this triangle, right? If this is, the hypotenuse is R and this is the base, so you can immediately get that your L is R cos theta. And so you can find what your H is in terms of the radius of this ring. Now, once you get that, you can immediately find the velocity because the amount of energy that is used by this mass to come from this point to that point, right? This entire amount of energy is what is used for this mass to gain its velocity. So initially it started from rest, and at this point it gained a velocity v, and so this entire energy will be balanced by the kinetic energy of this mass. So you can just directly write this equation. And now it's easy to solve, and you can get what our mv square is. Note that in this equation we need mv square by r. So I can just directly solve for mv square by r itself. And this will be twice mg 1 minus cos theta. Okay. Yeah.
Hey, excuse me.
Yeah.
For the energy conservation, do we write that for the entire system, or can I simply write that for a part of the system?
So, okay, so for that, you first have to define what the system is. So in this case, the only thing I'm concerned with is this motion of the masses. The ring itself is not suffering from through any dynamics yet, right?
Yes.
And also, there's no friction or anything. So you can write the total energy, of course, and then you can say write the sorry. So you can write a total energy, and you can write the energy of the ring, plus you can write all sorts of heat, plus you can write the energy for the masses, like the small masses. But this is not changing because the ring so far has no dynamics, and we are assuming that there's no heat loss or anything, so even this is not there because there's no friction or anything. So for this case, you can directly focus on these small masses only, because when you do, say, initial minus final, the only thing that will matter is the energy of the small masses. So is that fine? So you can only work with energies of the small masses, assuming that there is no interaction between these masses and the ring itself. So let's say because of the motion of these masses, the ring also starts to move. Okay, so let's say you have a scenario like this, where you have a mass and it moves till here, and because of this, the ring also displaces downward. So the ring also sort of acquires a downward velocity. So then the ring is now at this position. So then you can see that a part of the energy of this mass is also used to move this ring. So in this case, you have to include the contribution of this ring as well. So in this case, if you write, you will write that the mass has gained a kinetic energy. The ring itself has gained a kinetic energy with some different velocity, and all of this may be because of, let's say, the potential energy or some other kind of interaction that these things have. But here we are assuming that here for now we're looking at a static case where there's no interaction between these masses and the ring except for the normal force. So the only effect of these masses that this ring can fill is the normal force itself. So was this clear?
Can we also say that writing conservation of energy at the moment we are considering a system only comprising of these small m?
You can, yes, you can do it, but you won't be able. But okay, so if you write the energy conservation only, let's say you consider your system to be these small masses, right? In that case, you're assuming that the small masses are acting independent of this ring. That is, the motion of the small masses do not affect the ring at all. So in that case, you can treat them as your system and then write the conservation equation. But if they were interacting, because okay, so let's say the motion of this ring, the small masses impacts the ring itself. Then you will notice that if you write the if you write the energy equation for this, so it has an initial energy, and then it has some final energy, and let's say the ring develops some sort of heat, for example, or it starts to move. So you will notice that this equation is not exactly valid. Why? Because you have missed part of the energy. So part of the energy of these masses went into this heat development or went into the motion of this mass. So that you have to take into account. So let's say the kinetic energy of the mass or some heat or whatever happened. But in this case where we are assuming that none of this is happening, so you can treat these masses as individual systems and you can write energy equation for these masses only.
Okay.
So in Kleppner, for example, there is also one more example. Sorry, in Kleppner, there was another problem, and I don't remember if this was the setup. I think the problem was that you start, so this is a big mass, and there's a small mass attached here, and this mass starts to move. And because of the movement of the mass, this bigger mass also starts to move in the other direction. So there, if you write the energy conservation equation, you have to include you have to include the contribution of this part as well. Because then you have to consider the total system, the small mass system, and the big mass system. This entire thing will be your system, and you have to write the equation for each of them. Because this is exchanging energy with the bigger mass system, and so the energy of this one may not itself be constant. So you can have a look at these problems, and I hope it will be clear. So was this clear so far?
Yes.
Okay.
Yes.
Okay, good. So here again, we have seen that we are stuck with Newton's laws only because we needed what the V was, and there was no differential equation to solve for. So you can, for example, write, so if you remember, V is R theta dot, right? So you can substitute here and get an equation in terms of theta. But if you write in terms of theta, your n is still unknown. You still don't know how to eliminate L, the normal force. So the simplest way to get this velocity is via the work energy relation. And that will now supply you what this velocity is. And so you can work further through your Newton's laws. So for now, we can just substitute this part into this equation. So this is equation number 2. And you can get a normal, what the normal reaction is. So from this equation, the normal reaction will be mg So wait a minute. Okay. So this is this is 3 mg cos theta minus 2 mg, right? Because this becomes a plus, this minus will become plus, and you can add it to this term. So I can just take mg out, and I think I can write this as 3 cos theta minus 2. Okay, this is our normal force that we obtained using this work energy relation. So now, so remember that the purpose was to show that the ring will start to rise because of all these motions. And the equation that affect the motion of the ring itself are these equations, right? This particular equation. And in this equation, we needed this normal force, which is why we went and solved all these equations to find the normal force. So we can get back to our first equation. And okay, so I can write it here, I think. So this is, let's say, equation 1, and we had mg minus twice n cos theta equal to 0. Okay, now the ring, when will the ring start to rise? So the ring can rise, right, if this entire thing, so this is, when it is balanced, it is at equilibrium, right? It is just in the right position before it starts showing any movement. If this entire thing was greater than 0, then we have a net upward acceleration for the ring, right? So this equation is valid for this ring mass, and this can have an upward acceleration if this is greater than 0. So for that, we need to have that the tension is greater than all these forces. And remember, the tension is always greater than equal to 0, right? The tension, the string can only pull the ring up, right? It cannot push it down. So this expression has to satisfy this particular condition. So this will be true if the ring has to rise. And the task is to obtain under what circumstances the ring can rise, right? So there's a particular condition under which the ring can rise. And the condition in the problem is given in terms of the masses. So the mass of the smaller bits has to be such that it is greater than 3m by 2. So we need to show this part. So let's move forward with whatever we get. So for the normal force, we can just directly substitute 3 cos theta minus 2 cos theta greater than equal to 0. So notice that this is a quadratic equation in cos theta, right? Because of this and that, I'll have a cos squared term. And so for now, let's solve for the limiting case. So this is an inequality, and you can get an idea of the inequality if we solve for, at first, the limiting condition. So you want this to be greater than equal to 0. Let's first see when this is equal to 0. So for that, we'll get an equation, and we can simplify now. We can cancel these things. So cos square theta minus 2 cos theta to minus m over twice m. Okay, equal to 0. So this you can solve very easily. So this will be I think plus 2 by 2 into 3 plus minus square is 4 minus 4m. Right, this is just application of the quadratic formula. So, and you can just directly write as 1 by 3, and so this will be 4 times 9. So I'm taking this factor inside the square root. And so if I take this inside the square root, I'll have to square this factor. And this will be 1 by 3. Okay, let's try simplifying further. So then this will be 1 by 9 minus, we have, what do we have? 2 and 3, and I think this is a 4, yes, so 6, and yeah, I hope this is correct. So immediately you can see that for a solution to exist, right, for this above condition to be true, right, this has to be true if it has to rise. In that case, this has to be true. And so for a solution to exist, we need this quantity to be positive, or else there will be no solution to this condition. So we want this to be positive, either positive or equal to 0. So this is greater than equal to, and this you can solve, and you can take this into that side, and I think this is equal to 3m by 2. So I guess this was the condition. Yeah. So this is the condition. So this is what the ratio of the masses should be for the ring to rise. And you can find your at what angle it happens from this relation. So 1 by 3 plus minus. Now here is an ambiguity in plus or minus, right? I have to choose if it's plus or if it's minus. So how do you decide that? So if you look at the tension force, so the tension force in the limiting case, so that's when it's in equilibrium, it's given by this form, right? And you want the tension force to be maximum. You want it to be the maximum possible it can be for the ring to rise. And this can only happen if cos theta is increasing, because this is a constant, this is also a constant, and the only thing variable is cos theta, right? So this entire problem, the only thing that changes is the angle theta. So it starts from here, then theta will be this, and something else. So the only thing that changes is this theta, and hence cos theta. So you want cos theta to have the maximum value that it can take for the, the tension force to be higher. So for that we can choose the plus sign. There is another thing you can look at, and that is, so if you look at the limiting case, okay. So if, for example, this was exactly true, then the determinant vanishes and you have cos theta is 1 by 3, right? Sorry, not the determinant, the square root will vanish. For this condition, you have cos theta exactly as 1 by 3. Now, when will this limiting condition to be true? So again, if you look at this setup, so notice that as the angle is increasing, so as the angle increases, the cos theta decreases, and this tension forces decreases. And so when the angle is maximum, okay, this tension force will be minimum. This is because the cosine function, this cos theta function, it decreases with the angle up to pi by 2, and beyond that it changes the sign. So here it is plus, it's minus. So as the angle increases, this cos theta decreases and the tension will be minimum. And so for this ring to rise at all, the limiting case is that at least this much has to be true. And so this condition will be will correspond to the maximum theta. Now, if you solve for any arbitrary theta, if you solve for any, let's say, so we had this equation that cos theta is 1 by 3 plus minus 1 by 9. So we had this equation, and this equation gives you theta. So any theta you get should be less than the maximum possible theta, right? And this is only possible if cos theta is greater than the maximum value of cos theta, and that is 1 by 3. Cos theta at the maximum angle. And so this is another reason as to why you have to choose the plus sign here. So let me know if this part was a bit confusing. Was this part clear?
Can you please explain the second reason that you just explained for taking plus sign?
Okay, sure. So we first obtain the condition that if the ring has to rise, then this much has to be true. If this is greater than 3m by 2, then the ring will definitely rise. So so the limiting case is when m is exactly equal to 3m by 2, right? That's when the ring can rise, and if mass is less than 3m by 2, then we can see that there is no solution, and so the ring will not rise at all. There's no solution because the square root will become negative. So we have this square root here, and this will become negative. So the absolute limiting case is when you have this to be true. And when this is true, then the square root vanishes, and this gives you that cos theta is 1 by 3. Now, what will be that limiting angle? So this limiting angle, I'm saying, will be the maximum angle that these masses can take for the ring to rise. If it goes even beyond that, and then it's possible that the ring may not rise. So this is the maximum possible angle the masses can attain, for which the ring can still rise. So now, why is this the maximum? It's because, so when the masses are at this particular configuration or with some certain angle, let's say this is theta 0, and let's say this is also theta 0. So in this case, your tension is its absolute minimum, right? Because it is just at the condition at which the ring can rise. And the tension is given by this expression. And the tension can be minimum if cos theta is minimum. And we know that cos theta decreases with angle. So if this is theta 1 and this is theta 2, then cos theta here is less than the cos theta here. And so cos theta is minimum. So cos theta is minimum if theta is some maximum value. So from all this we can say that cos theta at the maximum possible angle up to which the ring can rise has to be 1 by 3. And we know that cos theta is a decreasing function, so cos of any theta should be greater than cos of theta at this maximum. This is true because any such theta should be less than theta max. And again, from this diagram, as you can see, that if theta is less than theta max, then the cos theta, for example, here theta 1 is less than theta 2, but cos theta 1 is greater than cos theta 2, right? So that means that any such cos theta should be greater than cos theta at this maximum theta, and it should be greater than 1 by 3. And for cos theta to be greater than 1 by 3, I will choose the plus sign instead of the minus sign. Was this clear?
Yes, it's clear now.
Okay. So in summary, what all we have done, because it was, I guess, a bit involved, so I'll just summarize once what we have done roughly. So the problem was to look for conditions under which this big ring M can rise. So what can you do for this is to understand all the forces and actions that this ring goes through. So you can write the Newton's second law by using the free body diagram, and we get this condition. And similarly, we can write the equation for the smaller masses m, and we get this particular equation. Now we have to find what the normal force is, and we can get from this equation. But for the normal force, you also need the velocity of these masses. And so here we can write the energy equation for these individual masses themselves, because this is for now stationary. So no energy of this small mass is being used anywhere, and all the energy exchanges of these small masses are happening among themselves. So only these small masses are moving around and nothing else is happening, no friction, no heat, and this is also not moving. So in this case, we can just treat them as isolated system, and you can write energy equation for these small masses. This gives us what the velocity was. From this velocity, we can substitute into equation 2 to find the normal force. And then to understand the conditions for which the ring can rise, we looked at the vertical acceleration. So this was the acceleration along the y direction, right? And we said that there should be a net positive acceleration if the ring has to rise. And then we obtained a condition such as this, and we said that the tension force is also always greater than equal to 0. And this then gave us this particular condition, and then you solve the limiting case. Fine, this is 0, so this becomes a quadratic, and then you find an expression of this kind. So from there you can obtain the conditions under which solution can exist, and this will be if the square root is positive. So this gives you the condition on this mass. And the angle theta, I think the simplest way to decide the angle theta without getting into any complication is that if you want your ring to rise, then you'd want your tension force to be the maximum. And so you want the cos theta value to be the highest value for this particular problem. And so for that you will need to have a plus sign here, plus some square root. So if this was clear, then I move to the next problem. This is a relatively easy problem. It might actually also come in your exams or something. So okay, so this problem is as follows. So you have a okay. Let's first start with another problem. This is this is more relevant for now. So in this problem, you have a pendulum that's made of wood, and you have an incoming bullet. It has mass m and velocity v, and this is mass v m. And this bullet will hit this wooden block at some time. And so the first problem is to find that how fast is the block moving immediately after the impact, right? So what can you do to find the velocity of this system immediately after the impact? So one thing you note that this is an inelastic collision, and by that I mean that this bullet will go and hit this mass, and it will also get stuck inside the mass. So initially we have a bullet, we have a wooden block. After collision, we'll have a system that is combined. So this bullet will be inside this block. Now, one common mistake that people do is you write the energy conservation equation for this. So you'll say this is the initial energy. The energy of this block at this position was, let's say, 0. Immediately after the impact, you will say that I now have a combined system, and this is kinetic energy and no potential energy, because I want the velocity just at the point of impact. Okay, so at the point of impact, this block has not started to move yet. So this is the point after, so let's say at t equal to t0, the collision happens. So I want what the velocity is at t0 itself. So then there's no potential energy also. So you can just do this, and so this is the final velocity of the combined system, because both the bullet and the block will move together. So this has velocity v. Initially, this is 0, and this is some final. So then you can say you can solve for v of f. However, this will give you a wrong answer. And this is because you have to note that when this bullet hit this wooden block, there are many things that happened. One is the bullet and the block formed a combined system. So a lot of energy went into deformation. Okay, so this is a wooden block, so of course it will get deformed, and this bullet will get stuck inside, and so a lot of energy goes into that also. Plus, there will be some energy because there will be friction between this bullet and the block itself. A lot of energy will be lost as heat also. So this is not the correct equation. The correct equation, if you want to use the energy conservation, you have to use the energy for deformation plus the energy for heat. And now this is a fully correct equation. Okay, this equation is fully correct, or plus some other things if there are. So sound. So a lot of energy will go into sound also because you'll hear a huge impact, and that of course comes from these energies only. Sound doesn't come out of nothing. And there may be some other things also. So you have to include everything if you want to work with energy conservation. And so this is not advisable at all. If you just write this much equation, then this is definitely wrong because you have these other contributions that you would have missed. So then what do you do? Note that even though kinetic energy is not conserved, your momentum is still conserved. Okay, momentum is of the system is still conserved because if you consider system to be this bullet and this wooden block as the entire system, then there is no external force. There's no external force on this entire total system. So you can use a momentum conservation equation, and the P initial should be equal to P final. And the initial momentum of the system only comes from the bullet because this mass is at rest. And finally, this thing will form a combined system which will move with a common velocity v of f. And so that gives you what v of f is. So you can easily obtain what the final velocity is right after impact. So this is So I think this is a natural way to do this problem. Perhaps most of you would have done this only, but I still wanted to mention this first point because a lot of times, so even if not in this particular problem, in a lot of other problems, you might just blindly use this energy conservation, and you have to keep in mind that in inelastic collisions or where you have deformations or you have bodies that combine into one body, so or you have sound friction or anything, then you cannot just blindly use these mechanical energy conservation because you have to take these factors into account. But momentum conservation here can be safely used, and this will give you what the velocity right after impact is. So this was the first part of the problem. So is there any doubt up till now? Just move this somewhere else. Okay, if not, then I'll move into the second part of the problem. And in the second part, what is happening is you have this block that moves with velocity v, and you want to find what the velocity of the bullet is. So suppose that you are doing an experiment, and after the collision, this combined thing will move somewhere here, right? So this is m plus m. And it will make certain angle theta. Let's say you are able to measure this angle theta. So let's say this is the maximum possible height that this block goes to. So if this was the center and this is the center, and then the maximum possible height will be this. So let's say this is the height till which this combined system rises. You measure this angle phi, and you want to know what this initial velocity of the bullet was. So how can you do that? Now, know that once the collision has happened, so after collision, so if you look at the system after this bullet has hit this block, then you can apply the conservation of mechanical energy, because whatever sound or heat or whatever energy was used have already been used, and now we have this combined system, and this combined system moves from say theta equal to 0, because at the point of impact, immediately at the point of impact, this block won't move, it will move after some time. And so it went from theta equal to phi equal to 0 to some phi equal to phi naught that you have measured. So you can write the energy conservation equation for the entire system after the collision, because after the collision there is no sound, heat, whatever. You only have the kinetic energy of this combined block, and the kinetic energy of this combined block is used to rise up to a certain height h. So for the combined system after the collision, so after all the heat loss or whatever has already happened, now the only thing that you have is you have the combined system, and you have the kinetic energy of combined system. And as the entire system moves, the entire system does not suffer from any other loss of energy, and all the kinetic energy is used to raise this combined system up to a height h. So you can write that the entire kinetic energy has been used for this gravitational potential energy. Now what is this h? Similar to the previous problem, you can find this h very easily. So let's say this was L, and the system came up to here. This was L, this is phi, and so the h is this vertical height, right? And so this vertical height will be L minus this part. So let's say this is L vertical, and this small part is nothing but L cos phi, and so then h is equal to L minus 1 minus cos phi. So if you put this here, then you can find that Vf square, and I can cancel these things, is twice GL, 1 minus cos phi, and the purpose was to find this initial velocity, so that we can do from here only. So right, I just substitute this part into here, twice Lg cos phi, and so then you can find what the velocity of the bullet was. So this is it. So are there any doubts in this problem? Or can I move on? Okay, so if there are no doubts, then I'll move on to the last problem. This is also from Klepner, and here we have, now this time we have to deal with the non-conservative force, that is the friction force. So the setup is as follows, that you have a mass that is attached to the spring and has spring constant K, let's say the mass is F, and there exists friction force between this mass and this ground. Okay. Now the first part of the problem is to, now imagine that if I were to stretch this mass up till some x maximum. So this is my 0, this is the x-axis, and I'm measuring from 0. So this entire thing is x maximum. And let's say the equilibrium position was x0. So and now let's say from this equilibrium position from x0, I stretch this block up to this x maximum. So what is the stretch factor? So this length, the stress factor is this quantity. And now the problem is that let's say I release the block from this position. Now in an ideal case where there is no friction, what would happen is that this is the equilibrium. I stretch the block till here. So the block will go, it will attain the equilibrium position, and then it will move back again. It will compress a little bit, and then it will come back to the previous position. Right, so the x initial and x final are going to be the same in an ideal case where there are no frictions. So there's no loss of energy basically. But in the event you have friction, so the block will come back, but it will come back to a point here which will be slightly less than the initial position of this block. So if you have friction, then it's possible that your final point, this, let's say this is x initial, is less than x maximum. So then there's a decrease in the amplitude, right? After one cycle, and by one cycle I mean that I release the block here, it goes to equilibrium, it goes back, and then it comes back again. So this is one cycle. And after one cycle, the block has suffered a loss, delta x, let's say, is S maximum minus xf. Okay, this is because of friction. So the block will not come back to its initial position. It will come back to a point that is slightly lower than x maximum. And if there was no friction, then the initial point and final point would be the same, and so there would be no loss. This delta x would be 0. So the first part of the problem is to show that this decrease of amplitude is the same for each cycle. So in the first cycle, we see that the decrease is delta x, and now let's say I release from, I start my block at xf. So I start my block here. For the next cycle, the block again goes there and comes back, and it will again come back to a distance less. So I have xf1 minus delta x. And so this is what happens in the second cycle. So the problem is to show that in each cycle, the delta x remains the same. So this can only happen if delta x is a constant, right? So delta x does not depend on how many times this block is undergoing oscillation. So this is what we'll show in the first part, that this delta x loss in amplitude is constant. So how can you do that? So again, here the reason the loss is happening is due to the work done by the friction, right? The spring system loses a certain energy because of the frictional forces. And so we can write, so the initial energy, or E of I, is the spring constants, half L square, where L is the amount I have stretched the string. And I release from the maximum position, so there is no kinetic energy. The xf final is, so it won't be L, it will be L minus some delta x whole square, right? So in the final position, this block will return to certain, so this particular spot. And when it comes here, the stretch factor is less. So this is, let's say, L prime, and L prime is L minus delta x. So then you can find the loss of energy that has happened. So in one cycle, this was the energy loss that this block has suffered. So what I've done is I've taken this L outside this square root, outside this square factor. So then I have a 1 minus delta x by L. And so then I can write this. I can take the whole square and write it as follows. So now we can see, so if I just multiply this, these two terms, so for the first term I'll have this, then I'll have half KL square times 2 delta x over L, minus I'll have half KL square times delta x square L square. So this cancels, the 2 will cancel and I can cancel the L, so I'll have 1 L here, so the loss will be KL delta x. And this term I can ignore. I can consider, so I can cancel this, for example, and I have half K delta x squared. So I can consider that delta x is much squared is much smaller than delta x itself. And I can, for now, I can just ignore this term, because this is a higher order term. This is a second order term, and if delta x is a small quantity, then this won't matter. This will be something very small. So then energy loss approximately is this function, and it depends on the decrease in amplitude. Now, from where does this energy loss comes from? It comes from the work done by the friction, right? So this entire energy loss has happened because of the frictional forces. Now here is something very important. Because friction is non-conservative, so this is a non-zero work. So what I mean is, normally what you have is you have this block here and you release it from some initial xi. So your initial position is xi and your final position is also approximately xf, right? The final position xf is approximately equal to xi itself. So in an ideal case where there is no friction, let's say, or there's no loss of energy, then this block starts here, it goes here and comes back to this position. So work done, as you know, is force times displacement. And this displacement, the net displacement in this entire journey is 0, because the block in an ideal case comes back to its initial position. So that amounts to 0. If we had any conservative forces, so let's say this is some F conservative, then the force will still, then the work done because of the conservative force will still be 0, because your displacement is approximately 0. Right, because the block returns back to its initial position, and so xf minus xi is 0. But friction is a non-conservative force, and so the work done by friction does not depend on does not only depend on the initial and the final points. Rather, as we have seen in the first half of the discussion, that it depends on the path taken. So this is very intuitive in the sense that if I'm moving in a ground that has some friction, and if I want to go from one point to other point, then we know that the total energy loss that I suffer will be less in this and greater in this, because this is a longer path. So it's a longer path, so I suffer from more frictional losses. So here is one example where normally this work done would have been 0 because my displacement is 0. I come back to my initial point. But because friction depends on the path, therefore the work done depends on the fact that the block started here, it came back to here. So let's look at the total path length of the block. So it starts from here and it goes back to the equilibrium point, and in it covers a distance L because that was the amount that was stressed. Then the block will go further and it will get compressed up till a distance here, that is a further distance L. Then the block again from compressed point comes to the equilibrium point, and from equilibrium point it goes back into the initial point. So this is further 2 more L's. Now this is approximately true. Of course, if you have friction, then you have L, and then you have L sum minus delta x1, because this compression won't be exactly L. There will be some loss here also. Plus there will be some losses here, plus some losses here. And so in total you will have 4L plus some 4L minus some loss that is very small. So this for now I'm ignoring. I'm saying that delta L is much less than L. And so the total path length that this block covers is approximately 4L. In one cycle, it starts from here, it goes to equilibrium point, it compresses, comes back, and then comes back to initial point. So then what is the work done by the frictional forces? The force given in the problem is F times this entire path length that this block has traversed times 4L. Normally this would have been a final position minus initial position. But because friction is a non-conservative force and at every instant of time you lose energy, so this does not depend only on final minus initial position, it depends on the entire path length. Now that this part is over, we can find what delta x is. So delta x is approximately, these are all approximate equations, and this will be 4F by K. Right, and this is a constant. So what this means is that you start from some xm, or rather the amplitude of your oscillation. So you have spring, and I stretch it up to some L. This is xm, this is x naught. And so initially you were in initially the amplitude was L, so this was the total this is the total amplitude of the oscillation. After one cycle, the amplitude will decrease by some delta x, and after the second cycle, it will decrease by 2 delta x, and this will go on. So this is an arithmetic progression series, as you have learned. And so the second part of the problem is to find the number of cycles such that the mass will eventually stop. Okay, so you need to find the... Yeah, is there any doubt?
Yeah, I wanted to ask, why is it 4L? Are we considering 2 oscillations?
No, we're not considering. So what happens when you stretch a spring is, say, let's say I stretch it to here, right? Or if the spring system is okay, let's first look at only the spring. So initially, so what happens is that if, let's say I release the block from this position, right? So it will cover one distance of L and it will go to the equilibrium point. So this is x equilibrium. But when it comes to x equilibrium, it still has a velocity, right? It still has a kinetic energy. And so it won't stop in x equilibrium. It will move further until the kinetic energy is completely lost. So it will come back to something here until the kinetic energy is completely lost. Now, in ideal case, when there is no friction, this will be L. This is because of simple energy conservation. If there is a friction, this will be L minus something, but we are saying that this L minus, let's say this is L minus delta, we are saying this is delta is much less than L. So we can approximate it as L only. So at this point, the kinetic energy is 0, but the potential, there is still a potential energy. This is minus L whole square. And so this is plus half KL square. And now this potential energy will again be converted to kinetic energy. It will come back to the initial point. It will come back to equilibrium point. So this is another L. And again, here it has some velocity in the forward direction, and potential energy here is 0 because L, the Stretch factor is 0. This is at equilibrium. And because it has a kinetic energy in the plus x direction, this block will again return back to its original position, and it will cover another L in this entire process. So in one cycle where the block goes from here to here, this is equilibrium, and again back to equilibrium and back to here, the total distance is 4L approximately. In ideal case, it is 4L exactly, but if there's friction, there will be some losses here and there, and so it is approximately 4L. So was this clear?
Oh, yes, yes. Now it's clear.
Yeah, so a very simple example is a pendulum, for example. So it goes here, equilibrium, it will go here. And this is not one cycle, this is half a cycle. One cycle if it comes back to initial point, so again it will come back here and come back here. So this is L, so this entire thing is 4L. And the friction work will depend on this entire journey. This entire back and forth journey, it will depend, and so the work done is F times 4L. And so this gives you what delta x is, and delta x is a constant. This friction force is assumed to be constant in the problem, and the spring constant is a constant. So what this tells you is that the loss that happens, so this is the loss of amplitude. Okay, this does not depend on cycle number, right? So there is no parameter that describes what cycle it is going through. It also does not depend on L itself. If it had depend on L, then at every cycle L is changing, so then this delta x would be changing. But it only depends on F and K, and so it does not depend on the cycle at all. So we can say that the loss is constant at every cycle. So if this is true, if the loss is constant in every cycle, then initially the amplitude was L. After one cycle, the amplitude will get dropped to L minus delta x because of friction. At the next cycle, it will drop to a further delta x. So this is L minus delta x minus delta x. And this will keep on going. So we have an arithmetic progression of amplitudes. And say you want to find the number of cycles. So let's say the number of cycle is n. So you want to find the number of cycles when this block will come to rest. So it will come to rest if this block returns to the equilibrium position, right? So, and when the block comes to the equilibrium position, there is no stretch, there's no spring stretch. So the amplitude has to be 0. So what is the amplitude at nth cycle? So from this sequence of events, we can easily see that if this was the first, so this is sort of the 0 because this is where it starts. This is after the first cycle, after the second cycle, and so on. And so after the nth cycle, we'll have the amplitude to be delta xn. And the claim is that after nth cycle, the entire loss will be such that the block comes to rest. So the total amplitude of the block will become 0. And then from this you can find the number of cycles it will take for the block to eventually come down to rest, right? So it will keep on oscillating between here and here. After first cycle it will be less, then it will be again less, and eventually it will stop. So that you can find using L by delta x. Delta x, we know what it is from this particular formula, and we can put this here. This is 4f times k. L, remember, was the L max minus x naught was equilibrium position. So was this problem clear?
Yes.
Yeah.
Okay, so that's all I had to discuss today. If you have any doubts, you can ask.
Can we consider this condition as damped oscillation, kind of?
Yeah, yes, this is definitely a damped oscillation. So because the amplitude at nth cycle will become 0. So yes, and the damping is happening because you have this non-conservative frictional forces. If you had any other conservative force, let's say you had, so this is a scenario, and let's say this block was mass and it had some charge also, and just for forcing it, let's say you have an electric field also, Now there would be no loss of energy because the all these forces, electric and gravitational forces, are conservative forces. So the work done will be some force times displacement, and displacement will be zero because it comes back to the initial point. But because you have non-conservative frictional forces, you have some energy loss, and so this is indeed a damped oscillation. Okay, are there any other doubts? Right, so I'll stop sharing.
No, we don't have mid-sem 2. Yeah. Okay, thank you so much.
Thank you.